replacement exam. And today we're going to actually do something that's a little lighter than what we've been doing. Well, I don't know. I thought it would be nice to do on a Friday. I'm going to save derivatives of inverse trig functions for Monday. It'll be all the differentiation formulas, just the formulas. Yes. No, you won't have to apply them. It'll just be, you're just going to have to know them. Yep. Yeah, and you'll know the ones, so it's going to be on all the differentiation rules that you're going to learn up through Monday. Because on Monday, you're going to learn the derivatives of the inverse trig functions. Today, we're actually going to learn another little technique. You can use it all the time. There's really only one real need for logarithmic differentiation. But before I get into that, we've learned about 3 different differentiation formulas that involve an exponent. We know what the derivative of e to the u is, and you're going to fill these in. A to the u and u to the n. Okay, so you're going to fill in those, but every one of those differentiation rules involves an exponent. So think about what they are. You might have to look back, see what those are, and then think about which of those rules you would apply to each of these situations. Got it? All right, I'm pausing up. Oh, so the kids are just really thinking about this. And what'd you come up with the derivative of e to the u? E to the u times u prime. Oh, good. What about if it's some other constant other than e? A to the u. Times ln of a. Okay. Nice. Now, do we all see that this works even if the base was e? Because what would the ln of e be? Right? So it's the same rule. It would cover both situations. It's just special if the base is e. Okay. What about that old power rule? U prime? That's it? And what do you want to say, Tim? You were going to say u prime too? Is there something else with it? Jen? What's up? This one? All right, wait. So, say it again? No, it's just like, this is like u cubed. Like this n is an constant. Wait. I want you to have a second to get back on this. Okay. Yeah. Good. There you go. Yeah, all of these involve the chain rule. But the ones that people get confused with are these two. I don't think people get confused with e to the u because they see the e. But what you really want to notice with these, to use the a to the u differentiation rule, the base has to be a constant, and the exponent contains the x. That's the variable. So the base is the constant to use the a to the u rule. With the power rule, the u to the n, the exponent is the constant. When I say constant, no x's. It's just a number. Okay? It doesn't change. So with that in mind, let's decide which rule we'd have to use for each one of these. If you wanted to take the derivative of 5 to the sine x, so you can use e to the u, a to the u, or u to the n. Wait, Jerry, you had your hand up. A to the u. I like it. How about the one underneath it? Come on. What are you going to use for this one? All right, Jess. E to the u. Mm-hmm. All right, we got another one there. U to the n. This is u to the n. Oh, boy. Oh, boy. What about this one? Oh, you weren't fooled. I thought you were going to say e to the u because you saw an e. Come on, somebody was thinking that. All right, let's let's do this last one. I just have to see it. How would you rewrite that? Oh, 10 months ago. Sorry. Yeah, it's the tan of x to the e. So when you take the derivative, what's it going to be? E. Okay, yeah, you guys can all say it. Uh-huh. Wait, what's the exponent? E minus 1. Times what? Oh, yeah. Secant squared x. Weird, huh? So you see the difference. So no, we don't get one there. Later on we might, but, so you're feeling real good about yourselves, right? Oh, yeah, I can differentiate anything. Yeah. Anything with an exponent, right? Yeah? You feeling real sure about that? All right, what would we use? Let's look at this one. Suppose we want to find the derivative of x to the sine x. Can we apply the a to the u rule to find the derivative? The base is not a constant. So the answer is nope. The base is not a constant. I got you to feel a little good about yourself, and then. All right, well, okay, we got some other tools in our little tool belt here. Can we use the u to the n rule, the power rule? No. No. Nope. Why? The exponent's not a number. The exponent's not a constant. No way. All right, I didn't really translate that. The exponent is not a constant. I was trying to say way. Oh. Oh. Yeah, okay. That's good enough. I can spell any way I want. So for this, guys, we need something that's going to work when we have a variable in both the base and the exponent. And so I'm going to teach you a little technique called logarithmic differentiation. The only time you ever need to use it is in this situation. But you can use it anytime you want to find a derivative of any expression. But this is the only time you really need it. Boy, that sounds complicated. Logarithmic differentiation. No, that's right. So you could always use it. No. All right, here. So here's the thing. We want dy dx, but there's that whole variable in the exponent. I wish there was some way we could get that down. I wonder if I could cut it and paste it down or something, because it's up in the exponent. Yeah. Uh-huh. Yeah. Okay, he's saying with something we've done something like this with logs. How would logs help us? So wait a minute, you're gonna have to show me. So like in other words, if I just take the ln of both sides, saying take the log of both sides, how's that gonna help? Yes. Wait a minute. Are you trying to rewrite? Oh my gosh. Wait, are you trying to rewrite this in live form? You're saying that would just be the worst thing I think I've ever seen. It would be Here's, don't write this, kids. Well, no, I just like I can't even imagine. This would just be the hardest. It's not wrong.
The sun is out. We haven't seen it in like 4 days.
And then, meanwhile, I'm thinking, why is she staring out the window when we're trying to figure it out? All right. Oh. Okay, but here's the thing, guys. We know how to differentiate natural logs, right? We're very good at that. So can we use, I do think this was a good idea, taking the ln of both sides. Oh, shoot. All right, kids. Now I have to. No, we're back. Here's the problem. We want the derivative of x to sine x. That sine x up there was presenting problems. Taking the ln of both sides is a very good idea, but why? What can we do next? Right now? It will be. It will be. But here's my problem. But what about that sine x up there?
Bring it to the front.
Oh, finally. I wasn't listening to you. Actually, I did hear you say that.
No one has proof of you saying that.
I did hear say it. Yeah, whenever you have a problem, you have an exponent, you don't want it up there, you take the log of both sides and then you bring it down. That's one of the log properties. So the ln of y equals sine x times the ln of x. Now we can go with what Jared was saying. We can get dy dx. Right? We're looking, remember guys, we want dy dx. That's the whole goal of this. We're trying to find the derivative. So now we can find the derivative implicitly, because it's not y equals, it's ln of y. So now I need you guys to tell me, what is the derivative of the ln of y? What are we going to say, Karen? Yep. dy dx over y or y prime over y? What do you guys prefer? Yeah, ready? All right, and what about the derivative of the other side? Product rule, because I know some of you were not going to product rule. That was upsetting. Plus, what was it? Plus the ln of x cos x. Okay. Oops, I don't know what happened there. All right, so now we know what y prime over y is, but we want just y prime. I don't know, want to know what y. Nice idea. Let's multiply both sides by y. So, you know, when you multiply and it's more than a monomial, you got a binomial over here. Make sure you use parentheses. You want to multiply this whole side. Sine x, I could write it over x. That might be nice. Now, there's just one other step. There's a y in there. Do we know what y equals? Yeah. Remember in the beginning? Y equals x to the sine x. We're just going to substitute that on in, right on down there. Here, because we had y prime over y, so to get y prime, you would multiply each side by y. It's your turn. I hope I didn't get that. All right, so let's just so. All right, so you see what we did here? So again, this is the only time you absolutely need to use logarithmic differentiation. And again, that tells you what to do in the name. Logarithmic, take the log of both sides. Differentiation, then take the derivative. So you take the log of both sides, apply your log properties, bring that down, and then differentiate and solve for y prime. Just the only thing at the end, you're always going to have to substitute in for y, whatever it equals. All right, let's try another. Oh, wait, I did want to get this down the steps. So first step to finding the derivative using logarithmic differentiation, right, oh no, it's starting. Take the ln of both sides and apply log properties. Like bring the power down or whatever you have to do. For both sides. And apply, it's a little lower than I want it to be, log properties. Yeah. Okay, so that was our first thing. Once we did that, what did we do next? Differentiate, right? Take the derivative of both sides. So I'm just going to say differentiate. It is implicitly. Now, that's going to leave you with a y prime over y or a 1 over y dy dx, however you want to write it. So remember what we had to do? We multiply by y and then substitute in for y. So the last step will be, multiply by both sides by y. And then substitute. All right, now we can do another one. Oh. All right, yeah. Why don't you guys try to get the derivative of x to the x? There's one you would have to use it for. So try it and then check with at least one other person. Okay, I'm sorry, Jared. What did you just say? All right, okay. Well, that's embarrassing. That came up on the recording. All right, so what's the first thing you did? ln of both sides. And when you take the ln of that side, we apply our power property for logs. We bring down the x, right? We all got that far? All right, and then we take the derivative. What did you get on the left? And on the right? Oh yeah, this is just 1. Actually, let's write that. So we have y prime over y equals x times 1 over x is just 1. That's the ln of x. And then multiply both sides by y. Just remember, it's a binomial, so put it in parentheses. You don't want to just multiply part of it by what? Or distribute. Sure. And then I got one more thing to do. Substitute in for y. Y is x to the x. So the derivative is equal to x to the x times 1 plus the ln of x. Who got that one? All right, 3 people got that one. Now, the next one, I have to warn you, the next one. Well, here's the thing. It's not in parentheses 2x to 2x. The only thing that's being raised to the 2x is the x. Oh, get that eraser out. Who needs a big old eraser? I always do that. Nope. All right, guys, we're going to have to pick a way to do this. Either way is fine. Either we can just find the derivative of x to the 2x and double it, all right? The other way, if you take the log of both sides, and I'm just going to write this for a second. When you take the ln of the other side, 2x, do you remember the log properties, when you take the log of a product, you take the log of the first factor, what operation is here? Plus. Then you could use that other property and bring that down. You see how that's going to go? All right, so what we decide we're going to do is we're going to find, I'm going to call this u. I don't want to call it y again. And then I'll find a u dx, and then I'll just double it. All right, because I just, I don't want to. So let's say that u equals just the x to the 2x. So when I want to get dy dx, it's just going to be 2 times whatever I get for that derivative, the u dx, or u prime, whatever you want. All right, so that's what we'll find. Great. All right, so we want to find u prime or the u dx. We'll take the ln of both sides, right? So the ln of u, ln of x to 2x, but we're going to bring down the exponent. So it's a product. We'll take the derivative of both sides. What are we going to get on the left? U prime over u. All right. What about on the other side? Times 2. Let's clean that up a little. So we have u prime over u equals, what about that first term? 2, right? And I'm going to write that as 2 ln of x. That looks better. Okay, and we're looking for u prime. So what do we do next? Multiply side by u. So u prime equals u times 2 plus 2 ln of x. And finally, what did u equal? To 2x. X to the 2x. We could pull out a 2 there, too. Actually, if we pull out a 2, because we still have to multiply that by 2, right? So dy dx, I'm actually going to pull out the 2 first. So this is 2x to the 2x times, what would go in here? 1 plus ln of x. And I have to multiply that by 2, get dy dx. So 2 times 2, well, I'll write it out first. X to the 2x times 1 plus the ln of x. Our final answer is 4. X to the 2x times 1 plus the ln of x. What? Really? Okay. Which thing? Wait, pulling out the 2, did that bug you right here? I just put as a common factor in there. Oh, why did we have to call it u and to get the derivative of that? We would have had the log of a product. We would have had to take the sum of the logs. We were trying to just take the derivative of this piece, because we could do that with only having to apply the one log property, that power one.
But now you still have to go back to the sum of the blocks.
No, like in other words, we found the derivative of x to the 2x, okay? So the derivative of y is just 2 times that. Right? When you find the derivative of a constant times some other function, you just keep the constant and then multiply by the derivative of what follows. It's like half the product rule, the other half 0. So this was the way we decided we were going to approach this to avoid having that other y property. But where did I lose you over here? We were okay for this part up here, Riley? Or? Oh, when I was going to do it the other way? Yeah. Oh, yeah, then people said, no, we hate that. So we did it this way. We just found the derivative of x to 2x and then just doubled it. That's what we decided. They decided they wanted to do it that way. If we did it the other way, if you take the log, the ln of a product, you have to take some of the logs. I would have to break it up like that, and then I could apply my power rule. Kids didn't want to do that. So you don't have to do that this way. So this is the only time you ever have to use logarithmic differentiation. When you have a base to an exponent and they both contain an exponent. Right? The base and the exponent contain a variable. This is what you have to do. But kids, you could use this technique to differentiate anything if you know your log properties. Now, oh, that's the one we just did. I don't know if we want to do that one, or should I show you like on a boring one? Oops. This one? Nice straightforward one? Okay. Do that one. This will be quick. There's no other multiplier up front. I'm doing something different while you're doing that. So I'm going to just show you how it will work. Oh yeah. I just. Well, no, I'm doing a different problem. Like I'm going to show you that in a minute. I want to wait till you get it. Did you guys get this one yet? Did you guys already get it? The one I gave you? I did. Where'd it go? Did you get? Oh, I put the Y in the end. That's annoying. But if you put this up front, nope. This is the order of the. Doesn't matter. Yeah, the 2ln of x putting on top of the x would look nice, right? Say? Yeah, this is like a weird, and this is like a weird little topic. I can't move that. Oh well. Yeah, I could just move it over there, the other side. Thanks. Are there any questions on this one? No, if you didn't get it, I want to. So, okay, you took the log of both sides. You bring the exponent down. Okay. So ln of x times ln of x is ln of x squared. No, you can use the product rule. I know you like the product rule. No, you like the product rule, so I get that. But then I use the chain rule. What? If you used product rule, you would have had ln of x times 1 over x plus ln of x times 1 over x. You'd have two of them. Yeah, same thing. Yes. Yeah, you can put the 2 up here. You can put the 2 ln of x in the numerator. Yeah. Yeah. Oh, and you were saying that's why I wasn't even getting why. Guys, can I just show you something really that's neat? No one would ever use logarithmic differentiation for this, right? Like, right, it would be 3 times all this squared times 2. You could, though, use it. It would be weird, okay? But you could actually use it. You'll get the same answer. On the homework sheet, you only have to do logarithmic differentiation on the first two. The rest is review of other rules that we've done. Okay? Of course you don't want to go. Oh, I didn't do the summary, did I? I always forget to do the summary. Oh, I didn't fill in the summary. Oh, we should have filled this in. Let's fill it in now. All right, so if the base is a constant and the exponent contains a variable, use the power rule equal to, oops, the derivative would be n u to the n minus 1 times u prime. If the base contains a variable, and the exponent is a constant. And finally, use the process of logarithmic differentiation. Both the base and the exponent contains a variable. Very nice.